Uh, so Ivan's going to talk to us today about the Parallel Location and Exchange Library, PLE. And with that, over to you, Ivan. Thank you.
Okay, so there are quite a few similarities and with the previous presentation. So the paradigm we're trying to handle in PLE, which is parallel location and exchange, point location exchange, parallel location exchange, is designed to enable coupling between mesh-based codes using MPI-based parallelism. So we can do both volume with overlap and surface-based couplings, and we need to handle multiple couplings. Like in the simple illustration, we could have an inlet for a precursor flow, a fluid domain, those with some volume overlap, and a boundary exchange for conjugate heat transfer. So for each coupling, we build an MPI intracommunicator, so it's really MPI based, and most function calls appear as collective functions. We try to hide the details of the communication. And well, actually, we do use collectives, but not so many of them, so it could be easily extended to sockets, for example. I'll go a bit into the history to kind of explain what can be expected of PLE and why we've done things that way. It's a subset of it's actually a subset of the CodeSaturn CFD tool. So I won't go into a detailed CodeSaturn presentation, but just to say that it's EDF's main CFD flow solver. It's been developed since 1997, mainly really in-house with some collaboration. And in the UK, that collaboration is mainly with University of Manchester, especially historically the turbulence aspects, and quite a few people at STFC now. And it's mostly based on a co-located finite volume approach, in which we can have any type of cells, including polyhedra, kind of like OpenFOAM, similar types of numerics, similar types of meshes. So that was clearly a design constraint, and parallelized mainly using MPI. We do have hybrid parallelization, but that's outside this. Well, we can talk about it for questions, but it's outside the main scope of the presentation. And it's been released under the GPL since 2007. So CodeSaturn has about 5 to 10 core developers. There's probably about, over time, over the last 20 years, probably about 30 people at least who've worked on it. PLE is a much smaller team. PLE, there's basically myself, one developer who worked on it, on some aspect of it some years ago. Our team leader who did some Python bindings recently, and one subcontractor some years ago who then went on to be hired at OnAir and who became the first developer of Sweepy. So that's, you see there's common ancestry there. And that's about all for the team. So it's not a full-time project. It's a subset of a full-time project. And the defining use case when that was initially funded was in a RANS LES European project. And the idea was to couple two instances of the code, especially a reference alias. So the requirements were really to have some to enable volume-based coupling of overlap, so a larger amount of data than what might be needed for simple surface coupling. On computers that were massively parallel and that didn't necessarily have that much memory per node. So that was also quite a strong constraint. And so to avoid bottlenecks, all stages of the coupling needed to remain distributed. So no central server, same as we've seen in the previous presentation. So the logic is quite similar there, and handle all type of elements. And that then the code used its own interpolation because we were doing co-located finite volume with no shape functions or such. And at the time, there was no freely available library that handled this. Some of the libraries which could inspire us were not freely available. And so in that context, we developed a library which is called FVM, Finite Volume Mesh, which was a subset of CodeSaturn, and which also included a data model. That library was released under the GPL, and that became also, it was, I think, used in Sweepy. I think it still is, but we'll see in the future presentation. And going from FVM to PLE was something we did, and that's really the main design point. When we started to add additional couplings, not just our code with itself, but wanted to add other codes, we basically had the choice between either copying data structures. We wanted to couple with Certes, whose data structures, were tetrahedral elements, but it's also needed to, it had non-interleaved arrays where we have interleaved arrows, like structural arrays instead of they have structures basically. And either we do extra copies or we separated the mesh model from the parallel scheme. So that's where we extracted the communication scheme from PLE and considered that all the data model aspects for the mesh model would be based on a type of callback logic. And that's basically where we arrived at the current architecture. I'll go a bit faster. For an example workflow, so a few important aspects is when we have parallel or partial overlap, we might exchange some values both ways. So each mesh will consider some local points at which we'll receive or interpolate distant variables, and the same mesh can also provide some donor portions of the meshes, local elements on which we will provide values to distant points. So the algorithm is symmetric, and basically if we couple a code, it can be used to couple the code with itself. And when we're dealing with the same variable, we don't need to say domain A talks to domain B first, sends to domain B first, and then receives. Everything is symmetric from the user. So we avoid deadlock issues there when we start going over to more than 2 couplings. I'll go pretty fast, but basically when we to have this portable and robust on many clusters, the idea is we use when we're coupling 3 codes as an initial scheme, we'll launch them each simultaneously using MPI, and then use an MPI comp split operator to split the communicator. And then we'll create some what we call a domains set, which is an object which can query different domains, and then we'll build communicators between each pairs of each coupling. Basically, if code A sees code B and code B sees code A, they'll each have a separate communicator. And then we do whatever further interpolation, and we have a coupling set object, which is basically something which allows synchronizing time stepping across codes. For example, here in the coupling, code A sees code B sees code C, code A doesn't directly see code C, but when we do time stepping or one of the codes says I need to stop, I'm finished, or I have a problem, or we continue, or let's reduce the time step, or any similar type of exchange, this lightweight object allows everybody to have a view of everybody else. So that's mainly for the time stepping aspect. It's minimalist, but it's quite useful. And so then the essential role of PLE is to assist in mapping from one mesh to another. And so this is done independently for each coupling. And we have a small, simple object, which we call a locator, which keeps track of this. And depending on whether meshes are static or mobile, this can be done once, or it can be repeated during time stepping. And same thing, we will be using the initial, once we've done the mapping, so which was here in the mapping, the location here is clearly the most expensive part. We'll see that in the following sections. And then during time stepping, we can just send the data along to the mapping. And so, as I was saying, PLE doesn't handle interpolation itself. It provides location info, and the code defines its interpolation. I'll talk a bit about the location principle, but I'll need to go fast on that because otherwise I'll run out of time. So in this example, I just have 2 overlapping domains. The gray domain is a RANS and LES is in green. And then I just have shades of gray or different colors for a simple parallelization. So here we'll see that some domains partially overlap, others don't. And we have the same type of bounding box logic that was shown in the precise communication. So select the centers of the couple cells, compute their bounding box, and also compute the bounding box of the, in our case, it's select center of couple set, but let's say it's select the points at which we're receiving data, computing a bounding box, and then we compute the bounding box of the donor or cells at which we're locating those points, exchange bounding boxes between all the processors. So that's something that's done by PLE. The bounding box themselves are done by callback. And then once we have that exchange, then we know that only those ranks which whose bounding box intersect need to talk to each other. And then we'll have a similar logic where we'll be sending coordinates of local points that are within the distant element bounding boxes to the corresponding ranks. Symmetrically, we receive coordinates for those ranks. Do a local point location. So the local point location is what's done by callback. It's not handled by PLE. It delegates that to the code. And we just return the best fitting element ID. So the simple logic we have is the location function should return something between 0 and 1 if we're inside the element, slightly above 1 if we're outside the element. So then we can compare results when we need to handle tolerances and we're slightly outside a mesh. And so in this case, I'll have a picture describing this a bit more later. So here we see that some points are within one domain's bounding box. A few other points are within another domain's bounding box. Then each point is assigned to the rank which returns the smallest distance for this point. And then the final information is a typo here. The final information, which is in exchange, basically gives a filter results indicating for each point to which rank it was really assigned. And then each rank, so each locator object, each local locator object, just simply maintains the coordinates of the distant points that it has received and the IDs of the local elements in which those points lie. And then we don't need the distance anymore. We can post-process it, but that's, and then discard it. And so the user doesn't see which point is assigned to which rank. This is hidden. They just know that they have a certain number of points lying in a given element to which they must provide values when we exchange data in whatever interpolation means we want. And then it's the code, basically when we exchange data, who should just queries this information and provide the values. So a few remarks here. We could use a few levels of hierarchy bounding boxes to obtain a finer representation of the mesh, and that could reduce the number of points to send to ranks whose subdomains don't contain them. But we need to keep the number of levels small so that the bounding box data itself doesn't require too much memory. And the number of neighbors and basically the excess points that are exchanged initially will depend on the partition quality. So to be safe, we currently use ordered blocking communications with send receive to limit the memory use. And then each coupled code should provide its own local point in mesh location algorithm. That's basically the equivalent of an adapter or another way of doing things. And there is in PLE some example code which can be adapted to linear and structured elements. Structured and AMR codes can probably provide some optimal search. We don't have examples of those, but they could probably do things much better. And if some unstructured code has curved elements, well, they'll need to provide their own implementation. But the good side is that they don't need for PLE to be able to develop that because they can use their own location immediately. A few optimizations for that. Since we're doing that order send receive, just to make sure we don't have too much data in flight at the same time and too much memory use, we have possible serialization. For example, in this 1D case, I could have full serialization where rank 7, for example, needs to wait for all the initial communications to be done before it starts, before rank 6 can talk to it, and then it talks to rank 9. So this could lead to strong serialization. In actual 3D cases, it's not that bad, but it could happen. So we recently added some communication ordering optimization, where basically we're doing binomial type approach, where in the previous example of 10 ranks, all the first 5 ranks will communicate first between each other, and the ranks 5 and 9 first between each other, and then so and so in a recursive manner. So in this case, we still avoid deadlocking, but we ensure that we have at least some parallelism. And a few additional features is that when we're exchanging metadata for mesh location, PLE can also exchange minimum and maximum preferred available algorithm versions. So even if some code has a slightly different version of PLE, and then there's a new algorithm in one of the codes, but not the others, the PLE by itself should be able to agree on whatever is available. So that's more or less a safety mechanism. And mesh location can be extended. We can basically expand the mesh location using a larger tolerance. So when we want to locate points that are not really inside a mesh, but close to a mesh, we can first locate points within a mesh with a given tolerance, then extend that. So we'll be testing the location on more elements, but usually with a smaller subset of points. And then locally, we can allow querying which points are located or not. So when points are lying outside the domain, well, the user decides whether that's an error or whether they can handle the situation. So a few essentials of the API. So that the data model is really kept to a minimum. And so PLE, as I touched on it before, PLE delegates all the point location operations to the call program. So there's basically 2 ideas: a function returning the extents associated with local mesh elements. Right now, we're just using the global extents, but the versioning and arguments are done such that we could have a finer grained option without changing API, so that if we improve algorithms on that side, we could exploit that. So that's a recommended practice. And then the function locating a given sets of points on a local mesh. So I'll skip on the function prototypes, but basically it's very simple. So you need to write your own functions based on your own data model. But that's all PA, and that's basically what's the equivalent of an adapter for PLE. And the fact that the code should provide a distance allows handling location aspects. So for example, here, the distance array should return a distance associated with a current location element. If it's negative, it means we haven't located the point yet. If it's greater than 0, it's been located. Between 0 and 1, it means we already found the point inside an element, so there's no need to do a finer search. If it's greater than 1, it means it's very close, but maybe not quite within it, so it might fit better to an element. So we see here the green point will stay to the given mapping, and depending on the order in which we test for different domains, the white point might be located on the dark gray cell first, but then when we see that it fits better in the light gray, that the final assignment will be the light gray cell. And interpolation, it's deliberately not a feature of PLE, as that really depends on the discretization used, and so in our case we can use simple schemes. So I'll skip on that. And just a few examples of applications. We can couple a domain with itself. There are quite a few internal applications of PLE inside CodeSaturn. So in CodeSaturn, basically everything that's adapter-wise is built in, and we can also use that for turbomachinery applications, for some fluid solid coupling. And there's a lot of coupling with the Certes code at EDF, and that can be on cells. In some cases, the mesh sizes are several hundred million cells, even a billion, and quite a few thousand processors in some industrial cases. Performance results, I'll go very fast to leave time. But basically, we do have measurements over the time PLE takes in a given case, and we can also separate the communication time for the other time. So when we do have load imbalance, we can try to see which code is waiting on the other more, and I'll also help that. But here we did a simple test case, which is very generic. So basically did a remapping of a field from a mesh to itself using different partitionings and using a volume mesh for 200 million cell mesh. So when we look at the scaling, we have some cases where we can have periodic mesh where the mesh basically loops around itself, which can make the bounding boxes a bit more complex. We have cases where we have the optimized ordering or not. So we see there is quite a bit of sensitivity to the balance. There is some noise here, and we're definitely not scaling linearly, but the scaling is not too bad, and we're still improving on large cases, and the total time is really not that large in this case. And when we exchange values, it's much simpler because in this case, we basically are just doing sends and receives. And when we don't have too many ranks communicating with each other, we can set a threshold so that we revert to asynchronous calls. So it's basically just the same thing as a Halo exchange or such. So that part basically has whatever performance the MPI library and network can give it. And we did test an alternative evaluation using another octree-like structure, which we have in code Saturn, similar to an octree, but for bounding boxes instead of points. So that's uses a bit more memory because we can need to handle overlapping aspects. And when we do use such a tree, if we did use such a tree actually in PLE, the point element matching would be done at a finer grain, so we would need to send that many extra points to some domains, and we could do a single pass for location instead of multiple pass. So we checked at least how that stage would behave, and we see that we do scale much better. We tested it for different parameters of the octree thresholds, but we also see that the additional memory usage can be much higher. So there are only a few parameters, but there are trade-offs there, and so it is a future possibility. But there will be trade-offs. Other alternatives will be to use a KD tree. And basically, final remarks: it's that basically PLE's minimalism is both a weakness because it doesn't offer nearly as many optimized algorithms as some other alternatives like DTK and Trilinos. There's no element intersection which can be useful for quantity conserving interpolation such as that of met coupling. It's not easily compatible with true chimera type meshes because a point belongs to a single element, so we don't have many multiple layers, but usually those codes have their own built-in techniques anyways. It does require providing a local search function. That's basically equivalent to an adapter. And the scaling is reasonable for thousands of processors. Actually, probably okay for tens of thousands. It might not be good for hundreds and thousands. The strength is that it has really low memory usage and very stable API, so low induced maintenance. And it actually could be a good component in some more complete toolbox for some parts. It probably doesn't do everything, but it can be a useful layer. And its utility functions for communicator handling can be very practical. So for example, when we do a comp split, instead of using an ID, we can take a string. It's simple, but it allows us to take the directory of the case we're running on and a few minor tools like that. And thanks for your attention, and I'll take questions.
Thank you, Ivan. So as before, we use the Q&A. There's already a couple coming in. Just before we move to the ones on the Q&A, though, I had a quick question myself, if that's okay. So when handling the overlapping domain calculation, how do you handle the instance of a domain that's been decomposed using sort of a complex algorithm? So, in the image you showed there, obviously the decompositions of your domains aren't Cartesian. So
in this case, basically, it'll depend on the partitioning. We have PLE exchanges the point coordinates, but the elements stay on the matching mesh. So there will be some sensitivity to domain decomposition. And for example, we don't have any rebalancing aspects. So for example, when we're doing surface coupling, parts which don't have any surface cells won't participate, and only the parts that do have surface cells will work. So there's no explicit balancing. It's the balancing is strongly dependent on the partitioning.
Okay. I think that probably actually answers Xiaohu's question, which was the question in the Q&A, but for completeness, I'll ask it out loud. So for PLE benchmark results, are you assuming your meshes are balanced across different applications? So I suppose it's specifically for the benchmark results that you just showed.
Oh, yeah, that's specifically for the benchmark, because in actual cases, for example, for the surface coupling, one code being much faster than another, we can have one domain which is a few thousand processes and another which is a few hundred or a few tens. So and in that case, the meshes are not balanced at all. So we basically, the cost of PLE is quite low compared to the computation. So we'll do the balancing based on the mean computational cost. And then what PLE helps us do is that in the log file, we can check how long each code spent waiting for the PLE part. So usually, if one code is waiting longer in the PLE communication, it usually tends to mean that that code finished before the other and was waiting for results for sure. So then it can help. It means we probably need to put more ranks on the other code and less on that one, but that can help. But basically, the cost of PLE compared to the computations in our application is really very small, so it doesn't really count in that balancing aspect.
Thank you. And a follow-on from Xiaohu. Any idea how to implement dynamic load balancing in the future? Or any intention, I suppose, would be a better way of asking it.
But to do that, we'd probably need to go to objects more like the octree structure we have or such, or do some pre-balancing possibly before calling PLE. So that will complexify the algorithm quite a bit. That would basically be similar to what I've shown in the last part, where we can do an octree, which is basically what we do when we do mesh joining. So this is something that would definitely help balance the load, but in many cases it probably wouldn't be worth it. So that's the question: is do we want to go in that direction or not? That's kind of depends on the type of usage we want to do with the library.
Okay, thank you. Yeah, there's also hardware resource usage as well. Xiaohu points out.
Yeah, that's for the resource users. That's also why basically the goal of PLE was to prioritize memory usage and robustness, not using too many communications at a time in case we'd have interlock or difficulties with MPL libraries over speed. So that's basically been the fundamental. If it's fast but doesn't run, there's no point. So on the hardware research, there's no big there's nothing explicit relative to the hardware usage, except that we maintain as little structures as possible and just point clouds and partly serialize if we need to, so that we don't use too much memory. So I don't know if it really answers the question, but let's say it's a simple approach. Yeah.